consider magnetic helicity, and that was HM, the integral of A dot B on the volume of B, and remember the relationship between B and the vector potential A. And I promise you to consider this time Ampère theorem. This is not Ampere's law. It's another result by Ampère, and it is not so much known. So I'd like to tell you something about this, all right? So in order to do this, we consider a current, J. I told you I tend, for the purpose of these lectures, I will ignore physical constants, okay? So if I refer to Ampere's law, not the theorem, but the law, then Ampere's law is the law that relates magnetic field and density current. J is the curl of B, and because I'm ignoring constants, I write in this way, okay? Otherwise, you remember there should be a constant μ0 there to remind us of the magnetic permeability of the vacuum. I will ignore this for simplicity. It's a constant. All right, so this is Ampere's law. This is a current that flows around it, and we know that if this is the current, there is a magnetic field, the B, around the wire loop. Imagine to deal with the wire loop. Now, I want to show you something about this result of Ampère, which is an old result. I don't know if I wrote it here. Is 1823, and he went lost. You find it in books, but not so often mentioned. So I want to show you this theorem because there is something at the end that I hope you find interesting. Okay, so in order to do this, recall Biot-Savart law. It's an important law. It's an induction law. And the Biot-Savart law, we know it as the B at a point X is induced by the contribution. If I consider this as a current carrying loop, then is a line integral here of the elementary length along the L, cross product with x minus x star divided x minus x star to 3. This is a very important law. I remind you, x star is a point here, and x is a point here. So it is a P of x, and this is x star. Okay, so this is the source point, and if you like to think in terms of current, there is a current flowing on L, and this is the point where induction is measured by this effect. Okay, so we have the field here, and it would be like this, and like this, and like this. At a certain point we hit this point, and we measure the induction due to the current. Okay? All right, so this is a source point, and I call X the induction point. All right, now this is, we call it Biot-Savart law. In all books, it's called the Biot-Savart law, but in actual fact, it was discovered by Ampère. Ampère already knew about this law, and if you want to check this, it's a kind of tricky business. Why? Because it's written in French. Okay, of course, Ampère was in France, but it's a long discussion. You don't see equations. You have to read words and words. But then you discover that he knew about Biot-Savart law. Okay, so we start from Biot-Savart law, which we could call it Ampère's law as well. And what we do? Okay, first of all, a little bit of exercise here. I'm sorry, I forgot I. I is the current. I is the flux. Flux of density J, this current density, across the cross section, across the wire cross section. Okay, so this is the current density, and this is just the intensity of the current. So if we write this, we have we can rewrite the same integral in this form, dl. We have a cross, and then I call r just this x minus x star. Okay, so I have r here, and then I want to, you see, is an x minus x star divided by an x minus x star in mod. So this is a unit vector, x minus x star. I have an r squared, because I simply consider r unit vector as x minus x star divided by x minus x star mod. Okay? All right. So, okay, this is Biot-Savart. What we do with that? Well, we want to prove the following result, as I said, as a theorem due to Ampère. 1823, and it says that for a given unit constant unit vector E is fixed in space. It's a constant. It's just a vector, but it's fixed in space and time. Then we have an equality B. The field at the point X is given by the current intensity I divided by 4 pi integral over our wire current carrying wire, and then we have an E here dot dl cross r, and triple product r squared. Okay, this is just a one way to rewrite Biot-Savart, and what he discovered is that this is equal to the integral of a surface S, and this is the grad, the directional derivative along the new direction of what? Of E dot R unit vector divided by r squared in ds. What is this surface? This surface, imagine this is a wire, a metal wire where there is a current. You want to compute the field, and everywhere tells you, everywhere in books they tell you to compute the field like that. So you have to integrate on the shape of the loop. But Ampère found another way to compute this field. He said you compute this field if you integrate on the surface that is bounded by the loop. I anticipate something new here. The new thing is, but to compute this according to the surface is even more difficult. It depends, because same loop, L, but maybe a different surface, maybe this surface, like a hemisphere, any surface. So the point here is not that the theorem allows you to compute things easier, in an easier way. The point here is that you relate the effect due to a line to the measurement through a surface, whatever is the geometry of the surface. It doesn't matter the geometry. It can be this geometry, it can be this geometry. Any surface. That means that he probably didn't realize that there is a topological character associated with this result. A topological character. It does not depend on the geometry of the surface. And it does not depend on the geometry of the wire as well. In any given L will have a given surface, but there are infinitely many surfaces. This is one surface, this is a second surface. Or many other, infinitely many. There may be other here, other there, okay? So my point is not about the calculation itself, but is the interpretation. Interpretation of induction, very interesting, because it depends on the surface, but not on the geometry of the surface. On any surface that is bounded by the loop. Okay, we are going to demonstrate this proof. And in order to prove this, first we have to work on this expression. And this expression tells us, now, I didn't say, but this operator, this is the, how to call it, nu, is the gradient times normal to the surface. Maybe this one. No, unit normal to the surface, or this one. Unit normal to the surface. Okay? So this is just the standard grad operator dotted with nu. Okay? All right. So if we consider that, we can start. First, we consider r unit divided by r squared, and we notice that we can write it as the grad of 1 over r. Okay, if we take the grad of this, standard grad, we get that. So that we consider the cross product of r cross e, and divided by r squared. And by doing this, we have a minus. We consider this in terms of the cross product of what? Of r squared. We interpret r over r squared as the grad, so we have a minus here, grad of 1 over R, outer product with E. And this is minus the curl of what? Of cross product curl of E over R. Okay? You can compute, you can try to do these steps your own. Okay? You just basic vector calculus, if you like. All right. So where we go? We go here. Recall vector identity. Vector identity, and this is the curl, let's say, curl of the curl. Okay, so for a generic vector field A, we have this is just the curl of A, and this is the gradient of the divergence of A minus the plus equation for A. And now we apply this to our vector field A, which we take it as E to R. Okay? So we consider this, we apply that, and we get the curl of what? Of this. We use this to there, and so we have R, unit vector cross E, divided by R squared. And this is, we apply this, but now note that when we do that, note that the Laplacian of 1 over R is a 0. R, in other words, is harmonic. Okay, 1 over R is harmonic. So this goes, and so we are left with this, and this is minus grad of the divergence of what? Of E over R, and this is equal to the grad. We go the divergence of this, we rewrite it as E dot R unit vector divided by R squared. Okay. All right. Now we are almost done through all this. Okay, right, so where we are there. So now we started from, consider this numerator. So we have E dot dl cross R, okay, and we can rewrite it. Okay, I have, let me check, did I write R is, yes, because it's an R squared, sorry, should be a hat there. Remember, it comes from the denominator was r cubed with an r here. So I divided and I normalized with r. So that is a unit vector. So this should be a unit vector. And this, I can rewrite this as r unit vector cross E dl. I'm just rewriting things. So let's consider the integral. This becomes, by playing with this, is just r cross E dl divided by r. Let me go back to this. And this is the integral. I note, this is the line integral. So here, I apply Stokes' theorem. When we apply Stokes' theorem, we convert the line integral into the curl, and so we have a curl of what? Of RE. So we have R plus E divided by R cubed, as usual. And this, because of Stokes, we convert a line integral to a surface integral. Let me write it with a nu ds, okay? Like this. Where remember, nu is the unit normal to the surface. Okay? So this gives us integral of on S. This is on S. This is on L. We have, we go back there. Curl of is just this. So we use that. And we have E dot R unit vector divided by R squared. And this is dot nu ds. And the last line is integral over S of, well, this is the grad along nu. So this is the directional derivative along nu. Okay? Directional derivative along nu, so I have the directional derivative along the nu of E dot R unit vector R squared in ds, which is exactly that result. This is, as I told you, this is quite amazing. He, of course, in terms, I repeat, in terms of computation, he couldn't see any relevance. We are talking 1820s. Impossible to imagine that there was interest in surfaces bounding a loop. But nowadays, there is a great deal of interest because of applications, because of many things. So to convert a line integral to a surface integral, okay. But to convert that effect to something that does not depend on the geometry of the surface, that is quite something. And is the modern view, the topological view, if you like, of this result. Okay, so this is what I wanted to tell you about Ampère. And then I want to tell you something else that is also another piece of information. Another piece of information that you don't find easily, or probably in books. So, and is connected to topology again. All right. So this is my take on that. I want to consider again the Osabar in relation to another quantity. Let me erase everything. There is an interesting connection between this approach and something totally different that you may like to consider. Imagine that you have a wire made of metal, and then you put inside soap film water. A soapy water. So you put some washing liquid in the water, it becomes soapy, then you put your wire there. Suppose it's a circular wire, you extract it, and what you get a soap film. A soap film as a disc. You know, when you do this, you can create bubbles. Now, bubbles in between from the soap disc that you have in front of you, and then you do this, then a bubble starts to create. If you do a little bit, just you remove the flat disc to become something in 3D, a surface in 3D. Now, any of these surfaces would play the role of the surface I told you about Ampère. If you look for the minimal area problem, the minimal area of these surfaces, then of course you get into a very beautiful and difficult mathematical problem. Why difficult? Well, for a circle, it's easy intuitively to think that the minimal area surface is just the planar disk. But if you take the wire in any shape, for example, a knot, what kind of surface you would get? So try to do this. Take a piece of wire and just make a knot in it, then close the ends, then you dip it in the soapy water, and you take it out, and you look at what is the soap film that is bounded by this knot. This is an interesting exercise, and unsolved in terms of mathematics, by the way. It depends on the shape of your wire. Very, very interesting. Okay, so now I want to tell you something about Biot-Savart. Again, Biot-Savart, and its interpretation in terms of solid angle. Okay, I want to check that I didn't miss anything and I'm on time for this. So first of all, I have to recall what is a solid angle. Do you know what is it? Many of you, not so many. Do you remember solid angle? Let's recall the concept of solid angle. This is the analogous of a planar angle that we know. Let me give you an example. Suppose we take a sphere. Now I will I will do a hemisphere, okay, half of the sphere. I am in the center here, and I see an object of some surface. So suppose this surface is a little surface, it's an elementary surface, ds. It can be a big surface, it doesn't matter. It's just an example. And when I'm here, and I look to this, I project this to an infinitely large sphere. The universe. The universe. When I do this projection, I see, I don't know, a spacecraft, and they project it away as to infinity. Then I do the projection that is called the Gauss sphere. Same here. I take this unit sphere, radius 1, as 2 in mathematics, and I look at this, and okay, so I look at the intersection on the sphere of this object, Imagine that is distorted, okay. Then this is elementary contribution to the solid angle. The solid angle of a whole sphere is 4 pi. So surface of the unit sphere in what is called steradians is 4 pi. Of course, it's the radius. I'm taking radius here. Radius r equal 1. If the radius is not 1, is different from 1, we have 4 pi r squared. Okay, 4 pi r squared. So this is the solid angle measurement of this elementary surface. Would be a differential of omega. Okay. And how I define the solid angle? Solid angle is defined as a big omega equal the integral. Now we have suppose this is nu, the normal to the surface, and this is rho, unit normal from the center of the. So we have a rho times a nu divided by rho squared in ds. This is the definition of solid angle. Okay? Remember, there is an interesting point for you in physics. In 1930s, 1931, 34, Dirac, a British mathematical physicist, very well known, he was looking for a way to consider the existence of magnetic monopoles, poles of a unit magnetic charge. And we know today that magnetic monopoles have not been discovered. Indeed, we take a divergence of B equals 0, no monopoles. So if you put a charge here, like a magnetic monopole, what you measure through the solid angle is the flux of this magnetic charge, or something else, radiation, coming from the source here, through this object, through the surface. So the solid angle is a measure of a flux. If you put some physical particle, some source, at the center of the unit sphere. Okay, this is enough for the solid angle. And, all right, I want to tell you Biot-Savart law in terms of this solid angle. And what I do, I consider again a current carrying loop, wire loop, L. Okay? So again, we have our current, this is current density, so there is an intensity of the current flowing here, and my point, source point is X star as usual. I'm here, point P at the position X. So I want to compute the induction as before. Biot-Savart is always the same. So I want to compute this in terms of the induction of the field. Okay? Remember what I have here is the magnetic field lines that are all going around, and maybe they hit this point. Okay? And they close up. Right? And is there any way to express this induction of the magnetic field through the current in terms of the solid angle? What kind of solid angle? Well, it's similar to there. I see a surface here, and this is S, and the solid angle is this kind of thing. Is the amount of field of view from here to this surface. Okay? If the surface, imagine, fixed as a wire, you have a surface. If this wire with the surface goes to infinitely far away, far from you, this solid angle becomes small and small and small. Imagine that it's infinitely away. The solid angle is 0. If it is infinitely away, you can think that the induction that you receive is 0, because this is infinitely away. And then imagine to do the opposite, to take this wire, current in it, field induced, and then you approach it to you. It becomes bigger and bigger and bigger and bigger. Even if it's very close to you, this angle is very large, very large. It can be even enormous, almost covering half of the sphere, of the unit sphere of Gauss, or even bigger. So it makes sense to think of the induction at this point in terms of this angle, of this solid angle. Solid angle is just a way to measure the effects near you or away from you. But can we establish a relationship between solid angle and induction effect? And this is what I want to tell you. Okay, so let me go on. In order to determine the induction effect, of a charge wire on a point at X, this one, consider. We start again from Biot-Savart. Okay, we start again from Biot-Savart. B at X is equal. Now I rewrite the formula that you showed before. You remember I had the dl cross r divided by r cubed. And then I consider r divided by r cubed in terms of the gradient of 1 over r. We saw it, the formula before. So it can be rewritten as the intensity divided by 4 pi integral on this loop of what? Of dl cross, and then I use exactly the expression I just derived before. Gradient of 1 over, remember here, well, I can write it. We have an r, okay. I replace r, it's the usual thing, is x minus x star, and this r is just the norm of this, okay? So if you like, I can rewrite this as x minus x star, like this. And okay, so let me rewrite this. I just change the order there, and I have I divided by 4 pi as a minus inside, and now you can prove, just basic mathematics, you can prove that this quantity can be rewritten as the curl of the integral dl over x minus x star. Okay, right. Prove this, please. This equal to that. And then remembering, you should know this, that the grad, okay, the derivative is a linear operator. So the derivative of an integral is like the derivative of a sum of terms, and this is equal to the sum of the derivatives of terms. Okay? It's a linear operator, so it can go inside, outside the sum, so it's like the integral in the same sense. So we have that this is I over 4 pi, and this is the, I call this quantity, I give it a name, okay? This is a vector quantity, so I call it V of x. Okay. All right. So now what we do with this quantity? This is just a shorthand for B sub r. We consider again, as before, a fixed constant or fixed unit vector in space, E, and this is constant in space-time. Okay, there is a fixed vector, and what I do, I consider the scalar product of this quantity V, this quantity here, with E. Okay, yes, so we are here. From there, V is that one. We can write this as a line integral of dl dot E divided by x minus x star. So if we apply Stokes, again, what we have VE, we convert this line integral to the surface integral. So this is ds, the integral on ds, of what? Of, we can take the star gradient. I'll tell you in a minute what it is. And we can write this in this form, x minus x star. And this would be nu in ds, where nu, as usual, nu, so this is our rho before, and the nu is suppose, let me remove this here, and suppose that the nu is this, okay? Normal unit vector. What is this? Now the grad operator, the grad is, as you know, is dx along I plus dy, dy along j plus dz along the k. And this operator, this one, is with respect to x star. Okay? J and z along k star. So what I do is this, consider the induction point, as before, x, and this is given by x, y, and z, and the source point. And the source point is x star, and this is x star, y star, and z star. Okay? So it depends on which point you consider to take the grad of. So if I use this grad, then this term can be written in this form. And what else? I can rewrite this. As on S. I take this nu ds as this symbol. This is nu ds. And so I can rewrite it as grad star of 1 over x minus x star. Okay? And this, let me remove this. This is a dot E. Now, I want you to notice one thing. The unit vector rho, the radial vector, goes from here to there. But the r vector is x minus x star, and goes from this point to this point. So I need to introduce r star in the opposite direction. I define this as x star minus x. Okay? So that I go from this direction to the point towards the source point. So from induction point to source point. Okay. So what I do, moreover, because of this relation, because of that relation, I can state that this operator is minus the other one. Okay? This and that just change sign. Okay, so let's go back to v of x, which is defined here. And this is the integral of over the loop of dl on x minus x star Now I use the curl operator with respect to the source point to write this as the integral over the surface from there out ds over x minus x star. And this becomes the curl of, let me call this quantity W vector. Okay, we are almost done. It's a little bit tricky. Now we can write, now, almost done. We have B as I over 4 pi, and then we have the curl of of the cross product, curl of a curl of W. Okay? Okay, so now we already use again standard vector identity. Again, let me go there. Okay. Curl of a curve, again. If I reverse the orientation there, it's good to point out, let me go back once just to show you that because I have to consider the opposite orientation given by rho rather than given by r, I have to go from r to r, or if you like a unit vector r star, then omega of x becomes, you remember we started, okay, I rewrite it as a rho unit vector e unit vector, nu unit vector divided by r rho squared in ds, okay? This was the standard definition, and we want to rewrite rho in terms of r, but I have to reverse it because I have to go this direction, so I consider r star, so I put r star unit vector here, dot nu r star squared, and this is of course ds, and this is just what we know about r star. So just to be explicit, I rewrite as x star minus x, the usual dot product ds divided by x star minus x in 3, okay? We remember, we have to use this. Okay, so let me go back to what we were doing there. I just use the standard identity, curl of a curl, curl, I take the curl of W, let me use this, and I have this divergence of W, sorry, this is a vector, minus the usual Laplace of W. Okay, this is the vector identity we used before. And I have to sort out this Laplace. Remember that the Laplace of W, the standard solution is expressed in terms of delta, if you like, and minus x star, okay? Something, this is the Dirac delta function. And this is the fundamental solution we have from Green's potential theory. Okay, so if we use this and we use the definition of W there, we can rewrite this as gradient of integral over S. I'm now using the result here, and this becomes d dot ds divided by x minus x star, and plus. Now the Laplace, I have to use this condition, so I have a plus 4 pi integral over S. This is the solution, so I have a delta x minus x star in ds. Okay. In ds. Remember, ds underline, you know, ds is just new ds. Okay, so what we get from here, we get the following. Now, this term is minus the gradient of the integral x minus x star dot ds divided by x minus x star mod cubed, and this is 0. This is 0 because x star belongs to L and x belongs to S. So when I integrate over S on the x point, this is 0, because delta is different from 0 only when x is exactly on x star. So this goes to 0, we are left with this, but this, you see, you compare this with that, so there is a minus that goes away, so we are left with the gradient of omega. So if we go back, going back to b of x, this is I over 4 pi grad of omega. You can rewrite this as I grad of what? Of omega divided by 4 pi. Same thing. So this is the solid angle. This is the effect induced by the current. So you can prove that the effect due to the current is, okay, the intensity of the current is a constant, if you like, in the wire, grad of omega over 4 pi. Omega over 4 pi, omega is a measure of a solid angle, divided by normalized with the surface of the unit sphere, 4 pi. So now we understand two things. One thing is the expression of the Biot-Savart in terms of omega. Okay. And the other thing is that we understand that this 4 pi in front of Biot-Savart tells us that the integral is normalized with respect to the surface of a unit sphere. It's a geometric way of thinking of Biot-Savart, normalized with this factor 4 pi. 4 pi in mathematics occur in many, many contexts, and when you see a 4 pi, you have to think about the surface of a unit sphere and why that comes in the equation. And so this is one way to understand things. Okay, now I promised last item, last issue is a relationship with a linking number of all this. Well, I have to explain what I mean by that, but one thing at a time. We take it not from theory viewpoint, but we take it from a physical viewpoint and see how it goes. So the last part of this entry into topological field theory, the last entry is what I said, emergence of linking number. Okay, we saw, just to kind of summary, if you like, we saw that magnetic helicity A dot B in dV conserved under ideal MHD, ideal condition. Okay? I told you, remember, B is the curl of A. So it's a field times the curl, the field A times the curl of the field. Field times a curl. Then I told you there is another conserved quantity last time. I told you that also kinetic helicity. Kinetic helicity is conserved. U dot omega in dV. What is U is the velocity, what is omega is the vorticity, and the relationship is that vorticity is the curl of the velocity, U. And I said that this is also conserved in Euler equation. A field times the curl of the field. Oh, there is an interesting analogy, right? By the way, B is solenoidal, divergence of B 0. We took A with a Coulomb gauge potential, divergence of A 0. Vorticity by definition has divergence 0. And if we assume U to be divergence less, it means incompressible fluid. Interesting analogy. There is one more helicity. Oh, there are a few more. One more helicity that is conserved is this current helicity. Current helicity is the integral, cross helicity, sorry. This is magnetic, let me write it. Magnetic H, this is kinetic H. This is cross H. Cross H is the linking, if you like, the combination of U and B. Let me check, because I don't know if I have a note on this here with me. Okay, cross helicity I don't, but doesn't matter. So cross helicity is U dot B dV, and this is also conserved in ideal condition. And then one more helicity is used sometimes in astrophysical flows, etc., and is the current H, and the current H is defined as the integral of J dot B in dV. Remember, in ideal condition, J is just the curl of B. And because J is the curl of B, B is divergence-less, also J is divergence-less. They are all divergence-less vectors in this scheme. But this quantity J cross B, J dot B, is not conserved. Not conserved in general. In general. It is conserved under very special conditions. For example, if the volume goes to infinity, and some conditions on velocity, vorticity, field B, and current J. So this is the state of things, okay? I want to show you how linking between field lines comes out naturally in this field theory approach. So let me take a simple example, okay? Example to show emergence of linking number. And relation with helicity. So consider this example, as usual, as we did in this lecture. Again, consider a loop with a current in it, flowing like this. Now imagine that, I take the opposite direction for some easy, simple reason. And now I consider carrying current carrying wire loop L, and this is one thing. The other thing, imagine I consider a surface. Which surface? No longer this one, but a surface S, a mathematical surface. So consider mathematical surface like this one. Okay? And if I take this one, the current goes through this surface. The surface is pierced at a single point. Okay? A single point and a single loop. All right. So this is the loop L, this is the surface, etc., etc. Now I want to consider the current I with respect to the surface. Okay, so the current I is just J dot. Well, of course, the current is through the cross-section of the wire. Oh, that's for sure. But there is nothing else around it, so I can write it as the cross-section ds, where as usual, the nu is the normal to the surface, and ds, again, is just the normal to the surface in ds. There is nothing else, so of course it's the flux through this surface. And the flux through this surface, by Stokes' theorem, this is the curl, Ampère is just the cross J as a curl of B, and this is just ds. And because of Stokes, all this becomes the integral over the loop of what? Of B in dl. Okay? And I took, by the way, the right-hand side, the right-hand reference, because this comes out. So along nu, and so I imagine that the surface is oriented according to nu. All right. Now I want to make another example. So now consider a different situation. And the situation is suppose that okay, something like, oops, oh, it doesn't matter. Let me write something like this, and then this, and this, and now, okay, oh, sorry. Now the surface is the same. Okay, imagine that the loop L is making M, in this case two loops, two coils. L has now M coils, and pierces S in M isolated points. Okay? So this is one, and this is two for two coils. If there are many coils, it pierces many times S. And S is the same surface here. It's an abstract surface. What we get? Well, we get the following. That when I go to I is given by, this is just a BDL, is the same thing, but now it pierces many times. So the flux is all through the number of isolated intersections. So is integral BDL, same thing, along the loop, but now this is M times I. If I is just, if I, or J if you like, is the current, is the flux of current through the wire. It goes once, and then it goes twice, and then it goes many, many times. So it's M times I. And of course BDL is just a contribution. So what we do? Well, we do the following. Use for B, for the B field, use B sub R. Okay, if I use B sub R, remember I have Mi, let me rewrite here, Mi is equal to B sub R. I replace B sub R, okay? There. So I have the integral on L, and then I replace B sub R there. And B sub R must be given by a second integral along L. B sub R has 1 over 4 pi there, and this is L star, the element of length along the wire x minus x star, and this is dot dl coming from here, and this is x minus x star to the cube, usual B sub R. Now, oh, sorry. Okay. Now we have an I here and an I here. So we can do this. And we are left with M equal that. So we are left with M equal, well, 1 over 4 pi, double integral on the same L of that expression. Well, let me rewrite that expression as x minus x star dot product dl plus dl star x minus x star cubed, and this time where? This time x and x star are both on n. Okay? So dl and dl star are both elementary length on n. So it's a double integral on the same curve. Okay? Suppose I have made a mistake. I made a mistake, sorry. I want to go back here. Yes, sorry. I want to say this is on C. This is on C. C is just the border of S. And indeed, this is on C, and one of these two is on C. So dl is on C, and dl star is on L. So dl star is refer to the wire where the source points are, and C is the mathematical boundary of S. Okay? Right. So I have here C and L. Sorry. It's okay. It's an interesting problem when the 2 points belong to the same curve. When the 2 points belong to the same curve, we have another quantity. Is not what I'm going to tell you now, is another quantity of geometry. But x belong to C, which is the boundary of S, and x star belongs to L, which is our wire. Okay, and what is this quantity? And this quantity is M is the linking number between C and N. There's a link. And we can call this quantity M as Lk, that is linking C and N. And this quantity, linking number, is a quantity introduced by Gauss, 1833. And this quantity, linking number, is a topological invariant. Is a topological invariant. It does not change if you deform the link. You have not to cut it. You have just to deform it. And if it doesn't change, then it is very interesting to use it, because it depends not at all on the geometry. So you have not to compute any geometry. You just evaluate it from a topological viewpoint. So this is the definition. By the way, it is an interesting fact that Gauss showed to himself somehow that this is a topological quantity. Why I'm saying this? Because he never proved it. We don't have a proof that he observed, he wrote that is a topological invariant. He just wrote a formula, exactly like this, with a 4 pi there, same thing. 4 pi m equals this, and then he said this is a topological quantity, invariant under continuous deformation of the link. He wrote that on a page of his personal diary. So when he passed away, people discovered among his notes about this formula. So this formula was published, made public, in 1867, so more or less 41 years later, and then people started to know this formula. And the little piece of information for you is that Maxwell came to know about this formula in 1867 when it was published. People said, you know, we found this formula in Gauss' personal diary, and he states that this is a topological quantity. And Maxwell gave it a proof. He proved that this is a topological quantity in his treatise. So if you go to his treatise on electricity and magnetism, you go to the second volume, don't look for the topological word. Topology at the time was just beginning to appear. You have to look for geometry of position. If you look for geometry of position, you find many statements of Maxwell. And after the solid angle again, interpretation or definition and interpretation, he gives proofs of this formula. So Maxwell was very excited when he knew about the statement of Gauss. You know, Gauss, great mathematician, he stated that this is a topological invariant. So Maxwell wanted to prove it, and indeed he proved it. So it is a very remarkable thing. Now, you see, this formula is pretty complicated. And this is an element of length, this is another element of length. If you interpret, this is a cross product, so you can, let me tell you a few things about this formula. Maybe, I don't know if I have enough time. Hope so. A few minutes. So first of all, there is a relationship between what we said and solid angle. I don't have time to tell you about, but you can recognize that. You can think of ds, nu ds, an element of surface, and this element of surface you may think of dl cross dl star. Okay? And so this is an element of arc. This is another curve, another element of an arc, and together they form a surface, twisted. In this case, it's a twisted surface. And so when you consider the twisted surface made by these two, there is a crossing that you see. A crossing from one line to another line with another line. Let me give you an example of what I mean. Suppose, because this leads us to consider the linking number as sum over the crossings of epsilon r. And what I mean by that, very simple. 1, 2, and the other curve goes either below or above. If it goes above, we have a plus, and if it goes below, we have a minus. So above with a plus, if you like a -1, a plus 1 sign convention. And we can compute the linking number between two curves. Suppose we have a curve like this. Oops. Let me use a different piece of chalk. Oops. Okay, better. And this. Okay, I put orientation here, like this, and then orientation like this, and like this. And now I consider this crossing and this crossing. Okay? So if I consider, okay, like this, and like this, and now I apply this rule. And I apply this rule, I see a plus 1 here, plus 1 here, and I apply this rule, I see a plus 1 here. So this, the linking number between C and suppose L, the linking number between C and L is, according to this formula, a half of what? Plus 1, plus 2. So this is plus 1. Okay? Try, as an exercise, to do the computation here. Try. Try yourself. The same, okay, like this, and the same orientation for the red curve, like this. If you do omit the self-crossing, this does not count, and if you do the computation, you will see there is a plus 1 here, a plus 1 there, and then there is what? We have here, we have plus 1 here, and here is a minus 1. Linking number, again, plus 1. Why? Because the yellow curve goes behind, and then goes back. So it's the same as this. This and this are topologically equivalent. Okay? These are topologically equivalent. So this big formula here, correspond to that one. Okay? It's the same. Instead of doing an integral and then another integral on two curves, you just do that and you compute the crossings and that's it. So you don't need any big computation. You just project the curve on a plane, any plane you like, any plane. This or this doesn't matter. You compute the linking number does not change. Okay, thank you very much for your attention. Thank you.